charge for our topics. And most important thing is to go to a MOSFET site. I'm not using the Moodle at this point. So all the information will be posted on the MOSFET. And this is a site right here. You should write it down. I hope you can see the MOSFET isu.edu. There's no slash right here. This is actually more accurate site right here. MOSFET isu.edu /classes/SATO/ENGR120. And then you find right here ENGR120. This is a plan for CE session. So you click on then you see schedule. Let me see view. This is our plan. We're in the 10th week, October 26th, and Dr. Bruce Savage will speak about civil engineering, civil and environmental engineering. Then Wednesday, the Dr. Abraham Poor, he's the chair of the civil and environmental engineering, will come here to talk about the bridge design. We're going to do the bridge design and construction testing in these sessions. The third week, second week, third lecture, Dr. Jim Maha will talk about the geotechnical engineering. And fourth lecture, I will come back here and talk about environmental engineering and communication. We are responsible for communication section of this course. Then the fifth and sixth we will test your bridge you constructed. Right. So this is our plan. Details are here, how you are required to prepare summary of each lecture, except for the Dr. Abraham Poor's. His lecture primarily design of bridge. So because I don't want to spend much time on this, and details are here. How to prepare a summary report and how to submit. I even put the examples right here. So please read this. And if you have any question, please contact me. My contact address here, satochik@isu.edu. So this about, and turn it over to Dr. Bruce Savage.
Okay. Yeah, where is it? There you go. Yeah, no. All right. Okay, let me bring up the right presentation here. I put the wrong presentation in. And I'd like to tell you a little bit what we're going to talk about today. We're going to talk about opportunities in civil engineering. All right? For those of you that may know a civil engineer, some of this will be relatively familiar. Those that don't, hopefully I can give you some information about what civil engineers do. And before I get started, Dr. Sato, I think we can put this up on MOSFET, right, this presentation? Well, I mean, but you're willing to put it up? So as far as taking notes, you don't have to You don't have to write down a lot of stuff, but just a few of your thoughts, and then we'll post the slides to kind of help jiggle your memory a little bit, okay? So let me do a brief introduction. Bruce Savage, and I've been here for did my presentation just start on me right here? Okay, hold on a second. We don't want to get going just yet. Relatively new here at ISU, and I've had a lot of opportunities, though, and that's what I want to talk a little bit today is about opportunities in civil engineering, because civil engineering is just chock full of opportunities. For example, I've had the opportunity of living and working in multiple areas, multiple states. I was in Alaska for a while, Oklahoma, Pennsylvania, Louisiana, Idaho, Utah. Those are the places I've lived. I've worked in other places, did jobs in California, Texas, Georgia, Pennsylvania, Washington, D.C., Maryland area. And so if you like to get out and see things and you're willing to stretch yourself a little bit, civil engineering has a lot of wonderful opportunities. I worked several years in Oklahoma as a kind of a civil/environmental engineer, okay? And the firm that I was with, the group I was with, did a lot of water and wastewater projects. And I was the new guy on the block, so which ones do you think I got stuck with? I got the wastewater ones, right? So you gotta take things with a grain of salt when you're working with wastewater a little bit. Realize that it's very important. It's kind of like farmers. We need them, right? Because we want the food. And then we got to get rid of the waste. And so there's always going to be a job for people that deal with wastewater. But because I did so many of those projects, I got the honorific title around the office of turd herder. Yeah, and I'd say, well, it may be crap to you, but it's my bread and butter. Think about that. Sometimes when you work with those types of problems, you just got to go with the flow. You know what I'm saying there? But anyway, on to what really civil engineering is about, okay? Building a bridge to the future. All right, here we go. Early signs of a civil engineer, okay? If you were someone, you know what? I'm starting to get a little paranoid now that I don't have the right presentation up here. As a matter of fact, I don't. I apologize. I'll have to go back to my original one here. Okay. Here we go. Okay. So civil engineering, all right? We may not be rocket scientists, but we do some pretty neat stuff anyway. So, civil engineering, the oldest of all the engineering professions, and obviously started way back early in Italy. There were some guys working on a tower over there, and unfortunately these guys had a little bit of a disorder where one leg was shorter than the other, so this looked like it was straight up and down. But early signs of a civil engineer. If you're the type of person who likes to get out and get your hands dirty, and as a kid you like to play out in the sand and do whatever, and you could take sand and you could do something like that with it, chances are you might want to be a civil engineer or think about it. So what is the engineering profession, all right? When we talk about engineering, what do? Well, we take the knowledge of math and science and we couple that with good judgment. And taking those two together, we can take natural or materials. We can take materials from nature, wood, steel, and so forth. We can utilize those and we can put them in a productive manner. And from that, we can build things that are a benefit to society. A lot of the things that we do benefit society. It's infrastructure, it's environment, all those things is what a civil engineer may be involved with. So the question that I'd like to ask you is, do you enjoy working indoors and outdoors? Do you like to solve problems? Can you handle higher level math? Not necessarily saying you have to be a mathematician or necessarily that you like math, but you can just handle math. If you can handle math and if you want to make a decent living, then your answer is yes to those, and it doesn't take a genius to consider that you should consider civil engineering. All right? So, civil engineering, what is it? Well, it's the oldest of all the engineering professions, and civil engineers, they plan, design, and manage and construct and operate. They do all those different things. In fact, I've known civil engineers that have designed something, they've planned for it, they went ahead and did the design. The contractor said, you know what, I'd like to have you on my construction team because you You know the ins and outs of this. I want you to be the project manager, if you will. They get on board, they become the project manager. Once the thing is built, the city will say, you designed it, you build it, I'd like you to run it. And so I've seen civil engineers go from all the way of designing a wastewater treatment plant, building it, to getting hired by the city to operate it. Not very common, but it can happen. But they do all these things to society's infrastructure, okay? The things that we use every day. What is society's infrastructure? Well, society's infrastructure is the highways. It is the public utilities and distribution systems. It can be the railway systems. It can be the air and sea transportation facilities, buildings and bridges of all types, and environmental waste treatment facilities, and flood control systems. These kind of outline some general civil projects that you may work on as a civil engineer, okay? Now, what we're concerned about when we start working on these projects is we want to take public safety into concern. That's foremost in our mind. We want to make sure we keep the public out of harm. We're worried about the environment. We want to make sure that we don't harm the environment, we can clean things up. We consider the level of risk that is involved. We also talk about the consequences of failure. Because some things you just can't plan 100%, and what happens if failure does occur. For example, some dams in earthquake regions, if we were to make them earthquake-proof, it would cost billions and billions of dollars. So what we try to do is mitigate or minimize the risk. If we have an earthquake here, how can we minimize it so we affect as few people as possible? We talk about the economics. Of course, the almighty dollar drives everything, and so we want to know what things cost. And then the benefit to cost ratio. Is it going to be worth it? Is there value to doing this project? Okay? And, of course, we want it to look good. Okay? Within civil engineers, there's 7 sub-disciplines. And that's what I'd like to talk about for the majority of my presentation today, is what are these 7 sub-disciplines? What are the areas that you may be involved in as a civil engineer? You may be involved in one of these, just solely. If you work for a large company and become specialized, that's all you do. Or if you work for a small company, you may be involved in a handful of them. All right? So, 7 different sub-disciplines in civil engineering: surveying and measurement, water resources, environmental, geotechnical, transportation, construction management, and structural. Okay? All those fall underneath the general heading of civil and environmental engineering. All right? So let's take that and break each one of those down and talk about each one. So survey and measurement engineering. All right? What do these guys do? Well, they do land surveying, property boundaries, trying to locate where does someone's property line start and where does it end. Mapping and route and topographical. If you're going to put in a road, where do you want it to go? Well, you got to show the contractor where he needs to build that. Along with buildings and other facilities. You have to tell them, okay, this is where I want it, and this is where you should build it. Okay? Water resources engineering. What is that? Well, this is the planning, design, and operation of water supply and treatment systems. Things like reservoirs, well fields, pumping stations, treatment plants. Stormwater management systems, you know. Generally, the problem that we have with water is we have too much when it rains and not enough when it doesn't rain. So the question is how do we get the water out of there when it does rain so it doesn't flood us? And how do we store it so we have it in times of need? And we also work with groundwater, erosion control. All right, and now I have a little presentation here. Now just hold your horses, everyone. Let's run it for a minute or so and see if it gets any colder. All right? My question for you is, on average, across the whole United States, how many gallons of water do you think you use or the average person uses per day? Okay, think about that for a minute. Some people want to throw out some answers. On average, the average person across the whole United States, for domestic use, how many gallons of water does the average person use per day? What do we think?
50 gallons.
50 gallons. Anyone else? 30, okay. Think about when you take a shower, you're in there for 5 minutes, if it's a real short one, if it's a real long one, 30 minutes. How many gallons of water do you use during that? The wash machine, we got 30 and 50. Anyone else want to throw out some ideas? Okay, well, the real answer is 150 gallons. 150 gallons per day, per person, across the United States. And in some places, it's a lot worse. If you come out west, and you also include the watering of lawns, not agricultural land, but just simply houses that have a small lawn, you're pushing 225, 250 gallons per day per person, averaged across the whole year. Obviously, a good chunk of that's used in the summertime, but we use a lot of water. Washing your dishes, washing your clothes, showering, washing your car, all these sorts of things. And what it all comes down to is, do we have enough water, do we have enough clean water to supply the needs we need? All right? So in order to supply the needs, we have a lot of big reservoirs, a lot of small reservoirs that we use for storage to capture the water during the high runoff times and use it during the low runoff times. We can also use that for hydropower. This is obviously a really large dam. And let's see. You can see the people, move the mouse up here, you can see the people up in there. Okay. Dam that's fairly close, Hungry Horse Dam up in Montana. The water is shooting out the sides right down here. That's what we call deflector buckets. All right. Okay. And we have water flowing in the rivers. Okay. We're wondering how much water is going down the river, so these guys are measuring the water going down the river. Okay. Mississippi Diversion Project. This is south of New Orleans, restoring wetlands. We originally thought about 30 years ago that we wanted to get into those wetlands and dry them out, so we had that land available. And then we come to find out later on that those wetlands are also very useful for purifying and treating the water. So now what we're doing is we're going back and we're trying to restore those wetlands, let Mother Nature take back over, and use that as water treatment. All right? Okay. And I apologize, I ought to say this McNeese Engineering down here, okay, this is, once again, this is an old presentation. I can't find my new one. I was down, and McNeese is down in Louisiana, so I was involved a little bit with some of these wetland projects. All right. Getting the water where it needs to be. These are 4 huge box culverts right in here. We have a railroad we have to go under, so all this has to be engineered to be able to support the amount of water that needs to flow there, structurally to get it over there so the traffic can still continue, and environmentally so we don't hurt the environment. Okay? Guide levees, also to keep the water where we want it. Floods in Venice, all right? Venice, really old town, a lot of historic significance to it. The problem is it's been sitting on water so much that we're starting to get settlement. The soils underneath are starting to consolidate, which means that the city is sinking. So if we keep letting it go this route, eventually people that live in Venice and use these water boats to get around are going to have water on their first floor. They're going to be walking around an inch of water. Okay, and it's going to keep the rise. And the question is, well, how much is the city of Venice worth? How do we fix that? So this kind of gives you an idea of the outlay. We got a lagoon out here, the ocean, an entrance where the water can come in, and then we have this area, and the water flows through Venice. They use those little boats to get around, and so they came up with a concept. All right. Well, what if we can keep the water in the lagoon at a constant level? So even though the city may be sinking, if we can just kind of keep that at a constant level, everything will be good. So when the water is right around 1 meter, we're good to go. When it's less than 1 meter, we go ahead and let it drop. But when the water out in the ocean, out in this region, out here down the lower right-hand corner, gets bigger than 1 meter, then we actually have this little gate that pops up and keeps the water level inside. I'm sorry, that's well, changes. This is change of 100 centimeters. So it keeps it out of the lagoon so the city doesn't become flooded. Okay? So here's a drawing of that. We got waves out there in the ocean, and then the lagoon stays at a constant depth. The cost to do this, to create this inflatable dam that will go up and down, okay, $2.6 billion. Not cheap. But then again, what is the city of Venice worth? Probably quite a bit more than that in historical buildings. Okay? Environmental engineering. Well, what do we do in environmental engineering? Well, this is the planning, design, and operation of drinking water facilities, waste treatment facilities, which can include sewage, industrial, hazardous, and solid waste. So a whole bunch of waste that we need to treat in one way or the other. It can also deal with air pollution control systems. and the remediation of contaminated sites. So a whole big area that environmental engineers deal with. All right, a little bit of a concept. We're just, in the past, the attitude that society took was the solution to pollution was dilution. And we realized after a little bit that this isn't the way that we want to go, and we're dumping all this stuff out into the environment, and this is kind of just a little joke on that. You know, the animals say, okay, we're going to move it into your neighborhood, all right? But we've realized that we need to do a little bit better than we have done in the past, and so environmental engineers are tackling that challenge. And so we have huge wastewater treatment plants, where a lot of times the water that comes out of these wastewater treatment plants is cleaner than the water that they pull into the water treatment plant. Okay? In fact, there's a new concept out there. It's called from flush to tap. Yeah, think about that concept, right? Okay? But we're getting to the point where we can actually clean the water to where we can turn around and use it. It's kind of expensive, and we're getting better and better at it, but we are taking the bad stuff out of the water so we can put it back in the waterways. Okay? Pittsburgh in the 1930s, not a happy place to live. A lot of smog, very hard to breathe there due to the air pollution. Okay? And now we go to places where we have still mills, and they do a really good job of cleaning up the air before it goes out. Things like electrostatic precipitators that are used to capture all the fine particulate matter before it goes out into the atmosphere. We're not perfect, but we're getting better and better every year. Okay? Environmental engineers may also be involved with things like fish kills, figuring out why fish kills occur. Now, sometimes fish kills are just a part of our nature. When you get a reservoir that turns over and depletes all the oxygen in the layer that the fish live in, okay, kills the fish. So the question becomes, what can we do to remediate that so it doesn't happen? Geotextile liners for landfills. We put a lot of bad stuff in landfills, and we don't want that bad stuff to get down in the groundwater. So we'll actually go in and put a really thick, it's not necessarily plastic, it can be a plastic composite or a clay type liner, and we can actually weld that stuff, not weld like metal, but actually get it so it's seamed is really tight, and water going down through there, going down through all the soaps and laundry detergent, bleaches and so forth, will keep all that stuff contained in the landfill and not allow it to go down into the groundwater. Okay? Geotechnical engineering, what do? Well, this is the planning and design of soil and rock structures, earth dams, tunnels, embankments, levees, foundations, buildings, bridges, and highways. So if it deals with soil, a geotechnical engineer is going to be involved. All right? So here's a little bit of, we're pondering a poorly thought out design concept. All right? And you think that that's just a cartoon. What happens when it gets built? You can't see the signs there very well. The top one says management, the bottom one says employees. All right. So geotechnical engineering. This is a tunnel project over in Cairo, Egypt, where they have tunnel boring machines. Actually, rather than doing a big open excavation, they've created machines that they can set down in the earth and tunnel. All right. So these big white things right here, actually, that's part of the tunnel boring machines down here in the corners. They'll put those down in a shaft and then turn them loose like a big mole. They'll just grind their way through the earth, and they come back and support it, and now you have a tunnel for a subway, for wastewater storage, whatever you need a tunnel for, they can dig it. Okay? Here's an artist rendering of the Washington Convention Center. This thing has since been built, so if you go back there, you can find it. But during the construction, this is what it looked like. A geotechnical engineer would have been involved in figuring out, okay, what kind of supports do we need back here against this wall to keep that soil from falling in? All right? How much soil do we need to move? What kind of foundation do we need down here to build that building on top of it so it won't sink and crack? Another picture of the construction site. Okay. Pouring footings down on the construction site. Once again, you need to know how much that soil will hold. And this is kind of a fisheye view of the whole construction site. Okay. Transportation engineering. This is the planning, design, and operation of road and railway systems. airports and seaports, mass transit systems, and this is a very bad day in transportation engineering. You know, the reality of the situation is that we like to get to where we need to go, to work or vacation, fun, whatever, and we want good transportation systems. So whether that's airports, railways, or roads, we want to make sure that they work and they get us there safely. All right, so here's a picture of Seattle Seaport. Civil engineer would have been involved in designing that to get the ships in and out, get the people on and off. The Central Artery Tunnel Project in Boston, Massachusetts, when they built that, they figured there would be 190,000 vehicles going through that a day. And I think there's actually more, close to 250,000 vehicles going through it now. Okay? A lot of cars to transport. All right? Now this right here, this is kind of what I would consider the epitome of civil engineering. When you look at that picture, everything you're looking at there is a component of civil engineering. Now, we haven't talked about structural yet, but we'll get to structural in just a minute. But we got roads, we got buildings, we got power lines that have to be routed, telephone lines, we got water lines and sewer lines. Everything you need to live in that area, to live and work in that area, is shown in that picture, and a civil engineer would have been involved in that, making sure that the environment is protected as much as you can when you crowd that many people into that size of an area, treating the water, treating the wastewater, the whole thing. Civil engineers have a hand in. Okay? Rotaries for traffic calming. These are becoming quite popular around here in Pocatello, Chubbuck area. They've put 2 in and they're considering some more. Just something to keep the traffic moving but to slow people down. Airports. Civil engineers are involved in the design of airports, making sure that the runways are strong enough for the planes to land on, and the layout. They also do testing. We want to make our asphalt better and better. So there's places that actually will test different types of asphalt to see if they will handle the weather conditions and the road conditions that they have to undergo or hold up under. Okay? Take a lot of asphalt samples and test those. And here's an early experiment in transportation. Looks like a lab experiment you do in class, right? Okay. Construction management, construction engineering and management. So this is more on the, not on the hard design side of things, but more on the let's get out there and build it type of civil engineering, okay? So this is the planning and implementation of design. So we have another engineer that does design, and you're the engineer that's interfacing in between the construction workers. You're taking the design down there, you're saying this is what we want built. So this is bringing to life what is on paper. And it's more management, less analysis, okay? We also worry a lot about scheduling, making sure that we can get things built on time. We work with a lot of various trades, whether it's the people using heavy equipment, the concrete, the people doing concrete, the steel workers, the pipe fitters, whatever. You have to work with a lot of different people in the various trades. And then we, as an engineer, you got to figure out creative methods for getting the job done. How can I do something faster and cheaper and save my client money and just do as high as quality as job? All right? So, if you've ever heard this on a construction site, this may indicate that you need a construction management engineer. I've carefully thought out all the angles. I've done it 1,000 times. It comes so naturally to me. I know what I'm doing. It's what I've been trained to do my whole life. Nothing could possibly go wrong, right? Yeah. So if you hear those kinds of things on a construction site, you might want a construction management engineer out there to help work through some of those problems. All right. There's large projects in civil engineering. I think my slides got jumped out of order here. We're back to geotechnical engineering, where they're worried about building dams or levees. There's a specific way that you want to do that. All right. We've learned a lot over the past few years, and hopefully it's been good. I was talking to a person just the other day that lives up in Sugar City about the construction or the rebuilding of Teton Dam. Now, I don't know how many of you have been following that, but that's kind of a hot topic in the water resource area. Teton Dam obviously failed and killed some people, damaged a lot of property, billions of dollars worth of damage. and there's some people that feel like it ought to be rebuilt. Now, irrespective of which side of the problem that you, or which side of the equation you sit on, the fact is we learned a lot from the last one, and it was an engineering mistake that they didn't foresee, and now we know how to build them a lot better so we don't have that problem, okay? So in this case, we're moving mountains essentially. This construction project was down in California. It wasn't just another reservoir where they'd come in and build a dike to dam it up, but it turns out that it was 3 dams, okay? So let me show you here. So we had these mountains down in California, a lot of growth down there. They needed the water, so they built a dike across here to frame in these mountains. They had to build another dike right here, okay? And then way over here on the other side, they built a 3rd dike. So they built 3 dikes to make this reservoir. All right. Structural engineering. What is structural engineering? Well, structural engineering is the planning and design of buildings of all types, okay? Includes bridges, towers, dams, and power plants. You know, they're involved a lot with dams doing the radial gates. It's a structural component. That's the interesting thing about a lot of civil and environmental projects is that the disciplines overlap. You can't build a building, a structural component, unless you have a geotechnical engineer that tells you how much weight the soil is going to hold, what kind of foundations you need. All right? You got to get the people to the building, so you're going to need traffic engineers to do that sort of thing. All right. So, good question here. How do they know the load limit on bridges, Dad? And Dad says, well, they drive bigger and bigger trucks over the bridge until it breaks. Then they weigh the last truck and rebuild the bridge. You know, Calvin says, well, I should have guessed. The wife says, dear, if you don't know the answer, just tell him. All right? We don't have the kind of resources available in our society to do this sort of thing. Well, let's just go out and build it, and whoops, it failed. Build it bigger next time, you know? And so what do? Well, we use engineering principles to know how much that bridge or that building is going to hold. All right? Another picture of civil engineering, Chicago. You know, we could go to any big city in the world and take a snapshot, and you just look, and you see that structural engineers had a large hand in that. The architect may have designed what the building is supposed to look like. The civil engineer, the structural engineer, made it so the building would stand up. All right? Brooklyn Bridge, work of art when it was first built. And it took a lot of ingenuity, a lot of engineering to get it done. It was constructed in the 1870s to the 1880s. We built these huge towers. Okay? Unfortunately, there was a lot of problems. The cables weren't as strong as they could be, let me restate that. They weren't always as strong by today's standard. By those days' standard, they would, but they didn't have uniformity in construction. So occasionally cables would snap, and when they'd snap, if you were close by, it could, you know, slice right through you. And so a few other pictures of the bridge building. Okay. Eventually, they did get it built, and of course, it still stands today. All right. So things that we build as civil and environmental engineers, hopefully they last for at least 100 years, almost, it would be 140 years, right? Or I guess 130. We're moving into new areas. Not just the plain old, same old that we do all the time, but as humanity moves out into space, there's a demand for building space stations. And so we are constructing different types of composite materials that are lighter and stronger to get them up into space. For example, here is the structure of one of the space station components made out of a composite material. So a lot of work is being done, and you have to figure out, okay, how is this different than steel? How much stronger is steel than it? And what kind of constraints does this material have on it? Sometimes you take on some interesting challenges. Here's the Mishima Bridge in Osaka, Japan. It's 410 meters long, 40 meters wide. It's a huge old bridge. And it spanned way out into an ocean-going, or a boat-traveling region, and they had to figure out, okay, we want to get cars across here, but what do we do when these big boats come up? All right? And so they said, okay, we draw an artist rendering, the boat comes on up through there, and what we'll do is we'll have this bridge built on a boat itself. It's built on a floating pier. And so when we need to get it open, we'll just have a tugboat just kind of push this thing open. It pivots over on this other side. Boats can travel up and down through it. And then when we want the traffic to go across, we just push it back shut. Okay? Too big of a span for traditional drawbridge type bridge, and so we actually create a floating bridge that we can move out of the way. All right? They even built this thing. It was constructed like a ship in dry dock. So they built it on dry land, moved it down to the ocean, dumped it out there, and moved it. Okay? Now, I'm going to take a quick break here and jump back to my other presentation. Let me show you another bridge that was built recently over in France. Okay, this is the world's highest bridge in Millau, France. All right. So from this angle, you can see the bridge down here in the lower right-hand corner. And watch as this bridge is being built. Those are the piers that are being built out there. And over time, as they keep raising those piers higher and higher, some are moving a little faster than others. And they have the crane out there and they just keep lifting the forms up. Pour more concrete, lift them up higher, pour them out there some more. You kind of see the changing seasons, that this is work that has taken a long time to do. Getting way up there, up above the clouds. So they're putting those members out there, building this structure. And it was kind of interesting how they built this, is they built it back on land and then actually slid it into place. They would slide it out over each one of those piers. So these are the engineers out walking underneath to inspect it, make sure everything's going good. Now they're walking down the deck. Okay, the cables that were used to help support this bridge. They gave this bridge a super elevation because it actually curved around, and they wanted the cars to feel comfortable as they're traveling at high speed, so it had a bank to it. Okay, it's the highest bridge in the world, over 8,000 feet long, 1,100 feet high. And it rises 1,100 feet above the valley floor, weighs a lot, 400,000 tons, resists winds up to 130 miles an hour. Let's jump back to that just really fast. Cost over $500 million to build, and it shortens the freeway route by 60 miles. So rather than the cars driving down through this little village, and it took them a long time to get down through there, they built this thing, and that's what it looks like when it was done. Pretty impressive. Okay? All right. So let me talk for a minute about the civil and environmental engineering curriculum. Mathematically, we have the physical and engineering sciences, physics, calculus, chemistry, geology, materials engineering, and thermodynamics, electrical engineering. These kind of provide the support for the civil engineering program. And once you build a good foundation, you can then move on to the more engineering-specific topics. Things like structural geotechnical engineering. Mechanics, statics is what we typically start out with. Mechanics and materials. How do materials behave when we put them under loads? Soil mechanics, structural analysis, concrete design, steel design. Other classes, fluid mechanics, water supply and wastewater treatment, water resources, transportation engineering, engineering planning and project management. And at other places you may have a course on ocean engineering, and then to cap everything off, you got to do a senior design project where you use a lot of these different courses to build one final project. Okay? So within the 7 civil engineering disciplines, just to recap, we've got surveying and measurement, water resources, environmental, geotechnical, transportation, construction management, and structural. Okay? And this is a bad day on the construction site. All right? Thanks. Do you have any questions? I'd be happy to answer any general questions you have on civil engineering. What about Idaho Falls? Okay, well that's all I have for today. So thank you for your attendance, and I hope you enjoyed the section. Oh, we have a question here.
We had an assignment that we were supposed to turn in today. Do we turn it into you, or?
Turning it up here. This is from Dr. Emmel. Yeah, just put a pile up here and we'll make sure it gets to him. Okay? All right, have a good one.